I plan to cover two main topics in this talk, which are based on a selection of papers that we published over the last 4 years or so. And so the first part will look at iceberg calving transitions in the North Sea, and particularly in relation to ice shelf collapse during the last deglaciation. And the second will be on meltwater drainage over multiple glacial cycles throughout the Quaternary. So the first part of this tale already tells the tale of how colossal icebergs once drifted along the coastline of the UK, but more importantly, why this might matter for the future of Antarctica. And this is based on a paper we published back in April this year in Nature Communications. And I think I'll start this talk with a universally accepted truth, and I think all of us here can appreciate that everybody loves icebergs. They're beautiful. We love the strange shapes they make, and the intensity of that deep blue color when they're submerged underwater. We love the fiery silhouettes they cast across the horizon, and their brooding presence as they drift through the cold waters of the Southern Ocean. Everyone loves icebergs. Now, the media loves them too. So whenever a large one of these breaks off, you can guarantee it will make headlines all around the world, be that because of the amount of water they release, or the social media frenzy they trigger, or even the islands they might drift into. It's really hard to forget icebergs. Now, when icebergs drift along in the current, they often get dragged along the seafloor and leave a sort of doodle or a plough mark in the muds below. And some of these seafloor doodles can be as or even more striking than the icebergs that formed them, especially in these colourful bathymetric maps. Icebergs can produce some truly fantastic patterns, from crazy swirls to loop-the-loop patterns, and even some downright bizarre ones. But iceberg plough marks are not just pretty. We can actually use them to reveal really important information about the processes that have affected the retreat of ice sheets in the past. And also their drift can tell us about changes to ocean circulation in ancient times as well. But big questions remain as well. So in the last ice age in the UK, the country that I'm from, the country was covered by a massive ice sheet that bridged across the North Sea and spanned all the way to the Russian high Arctic. And we can use the glaciation of this ice sheet as an analogue for how Greenland or even Antarctica might respond to climate change in the future. But so far, exactly how the margins of this ice sheet collapsed, particularly over the North Sea, is not very well known. We know that icebergs were present in the North Sea in the past, but exactly what type and what role they played during the deglaciation is still quite poorly known. And that's because previously in the North Sea, we had data like this. This is a 3D seismic time slice of an ancient glacial landscape. And what you can see is the scours of these giant icebergs as chaotic lines. But the data are quite low resolution, so you can only really image the largest and deepest iceberg plough marks in this data set. So in our new study, we used a new high-resolution seismic reflection technique to examine the glacial history of the North Sea. And the way this works is that we fire sound waves from a ship, and these sound waves penetrate into the seafloor, and once they've penetrated the subsurface, they bounce back and reflect off all of those buried layers beneath the earth and travel back towards the ship where they're collected and processed. And what you end up with is this, a 3D seismic cube of the subsurface. And then what you can actually do is you can scan through all the layers buried beneath the surface of the Earth. And these can be thought of essentially as ancient buried landscapes, which you can then use to reconstruct how the climate and the buried landscapes under the North Sea have changed over time. Now, this is not a new technique, but what is really special about this data is the detail that we can see using the new data. So on the left image here, we have an example of a conventional 3D seismic cube, which you can slice through to reveal all the buried features beneath the Earth's surface. And this conventional data is good enough to map basic subsurface features, but we can't really see their shape or internal structures in much detail. If we then contrast this with our new high-resolution 3D seismic data, we can now see previously undetectable structures and even entire buried surfaces that were completely unresolvable before. Now, looking specifically at iceberg plough marks now, on the bottom panels here, we have conventional 3D seismic data. And you can see on the image again, a few plough marks as black lines, but also lots and lots of artifacts. And if we can compare to our new data over exactly the same area, we can see a huge amount more detail that simply was not resolvable before, both in terms of the number of features, but also their different patterns and geometries. Now, as these icebergs reflect the drift of ice in ocean currents, we can use these patterns to reconstruct the direction of ocean currents and eddies thousands of years ago. And sometimes you even think that these icebergs have a sense of humor because they draw patterns in the seafloor like this fish. And I think that is exactly when you know you've been staring at a screen for far too long doing seismic interpretation all day. So we mapped the iceberg plough marks in this new data and found three different types. The first being an individual V-shaped scour mark, which are formed by single fairly small icebergs, and also a second class of much broader marks, but again, formed by these singular plough marks. But the third class we found was quite different to what we'd seen before. And these grooves were wider and much more subtle, consisting of these comb-like structures with multiple sets of aligned grooves. And the more we looked, the more of these unique features we began to find. And there's only really one process that can lead to the formation of these cone-like plough marks, and that is the drift of giant tabular icebergs, like the ones that regularly make the news when they break off Antarctica in the present day. And this is therefore proof that giant icebergs once floated less than 90 miles from the UK coastline. But more importantly, as large tabular icebergs require full thickness carving from ice shelves to form, these multi-keeled plough marks provide the first direct evidence we have that ice shelves once fringed the margins of the UK during the last glacial period. So how big were these icebergs? Well, that question was actually harder to answer than you might think, because it's rather challenging to estimate what percentage of an iceberg actually touches the seafloor compared to its surface dimensions. So we were going to look at other locations where this sort of plough mark has been found before, in areas like the Canadian Arctic, the Weddell Sea, Barents Sea, and also the Norwegian margin. And this showed that these multi-keeled plough marks tend to be less than a few kilometers wide, even in areas where these giant megabergs are regularly produced today. And this suggests that the plough marks these icebergs leave behind are generally several times smaller than the dimensions of the iceberg that form them. So given that the widest iceberg plough mark we see in the North Sea is about 2.5 kilometers across, we conservatively estimate that the icebergs are at least 5 kilometers wide, but probably were more likely to have been a few tens of kilometers wide. And that is easily enough to cover a mid-sized UK city like Cambridge, and you've got the British Antarctic Survey being covered by a giant iceberg in this image here. In fact, when we compared the inferred size and also the keel depths of our North Sea icebergs to those carved from modern Antarctic ice shelves, we found that the ice shelves in the North Sea were probably similar in size to some of the smaller modern Antarctic ice shelves, like the Brunt ice shelf, or this is the Ekstrom ice shelf at Germany's Neumayer station, shown in the picture that I took here a couple of years ago. And in fact, whilst we're at Neumayer station resupplying the base, there was this huge tabular iceberg floating just offshore. And so those of us who were working on this paper at the time would stare across the bay in the evenings and wonder if this would have been a similar site just offshore of Scotland a few thousand years ago. Right, so the image of giant icebergs floating less than 90 miles from the UK coastline is, of course, a really fun story. But why does it matter for? So today, a large portion of the exterior of the Antarctic ice sheet is buttressed by ice shelves, the yellow areas in this map. And in a similar way to how buttresses on a building support a much larger structure, these ice shelves act to hold back all of that ice as it tries to flow out towards the ocean. Now, the type of iceberg carved from these ice shelves reflects how stable they are. So relatively stable ice shelves produce these gigantic tabular icebergs every few decades, whereas rapidly retreating tidewater glaciers produce lots of little tiny icebergs very frequently. And sometimes a change in, say, ice flow behavior or increased melting can change the structural integrity of an ice shelf, shifting it from a stable carving pattern to a rapidly retreating ice front. And we've seen this shift in carving regime play out in other ice shelves around Antarctica before they rapidly collapsed, the most famous example being Larsen B in 2002. And once an ice shelf is then lost, its buttressing effect is removed immediately, which can cause the ice held back behind it to speed up and contribute more to sea level rise. So how does this fit with our data? So if you remember back to earlier, we can scan through all the different layers beneath the seafloor to look at how these processes changed over time. And if we do this, we find that around 18,000 years ago, our multi-keeled landmarks disappear and are replaced by much smaller chaotic patterns. And so the disappearance of those giant tabular icebergs happened around 18,000 years ago. And this suggests that a similar regime shift happened in the North Sea around this time, with the style of iceberg carving shifting from the production of giant tabular icebergs to the rapid carving of numerous smaller ice blocks as Britain's ice shelves disintegrated, just like for Larsen B. Now, the British-Irish ice sheet began to deglaciate around 22,000 years ago. So that's thousands of years before we began to detect the shift in iceberg carving. However, the loss of its ice shelves around 18,000 years ago did coincide with the collapse of the ice sheet's marine-based sectors and also some of the fastest retreat rates the ice sheet ever experienced. But the eagle-eyed of you will have noticed that we've got a bit of a chicken and an egg situation on our hands here. So was the ice shelf breakup the main driver of that accelerated ice shelf retreat across the North Sea? Or did disintegration really come forward as a symptom of enhanced mass losses that were already underway when the ice shelves collapsed? And because our dating constraints in the North Sea are not that precise at the moment, we need to do more work to fully answer that question. Which order did this happen? However, what we do know is the loss of Britain's ice shelves probably had a very significant impact on the retreat of the ice sheet, especially in those relatively flat-bedded and retrograde areas of its bed. And that's because recent work has highlighted how ice shelf thinning, iceberg carving, and sea level rise can trigger these very rapid pulses of grounding line retreat across quite shallow gradient or retrograde areas of the bed, especially once contact with these stabilizing topographic high points is lost. And so it's possible that similarly high rates of ice retreat were promoted across the central North Sea in response to the ice shelf disintegration. And given that very large areas of the modern Antarctic ice sheet are grounded on similar bed conditions, this certainly is a lesson that could be relevant to the future of the Antarctic ice sheet too. So that's part one of the talk. And I'm going to move on to the second part, which is to focus on the second story that this data can tell us. And that's all about how water used to flow beneath ancient ice sheets and what this can tell us about the future of Earth's remaining ice sheets today. Now, the context of this work is really the dramatic changes that have affected the Earth's remaining ice sheets over recent years. So over recent decades, we've watched as these giants of the climate system have woken up and have begun to contribute increasingly to sea level rise. So these videos, you can see red colors areas where ice is being lost and is not being replenished over both the Greenland and Antarctic ice sheets. And in Greenland, where this image was taken, we're beginning to see years where the surface of the entire ice sheet now thaws for multiple days a year. And all of this melting generates gigantic, huge rivers, thousands of them, each of which is capable of releasing more energy than the world's largest hydroelectric power dams when it falls through holes in the ice sheet surface and plummets down to the plumbing system of the ice sheet below. In fact, this water is so powerful that it can lift the ice up from the bed, making it slide faster towards the ocean. Now, you might think that Antarctica is conversely too cold to melt, and this is partially true. Surface melting is more restricted to the ice shelves that fringe the continent, but melting is only predicted to increase further as the climate warms. And the meltwater features you get here are still absolutely spectacular, such as this enormous waterfall cascading off this ice shelf. So meltwater is affecting Antarctica, have no doubt, and it's only going to get more important in the future. So water is therefore incredibly important in determining how ice sheets flow and ultimately will drive sea level rise in the future. And this begs the question, if these massive melting events are happening already right now, what will happen to these ice sheets in the future when we're faced with significant climate warming, say here or here or here? We need to urgently understand how the plumbing systems of ice sheets will respond to climate change. But because the satellite record is quite short, we can turn to glacial landforms produced by water during the growth and retreat of ice sheets in the past for a longer-term perspective. And in particular, we can examine the remains of vast rivers of water that used to flow beneath ice sheets as they deglaciate. And these are called tunnel valleys. Now, tunnel valleys exist across large parts of the world that used to be covered in ice during past ice ages. We've got some examples here from North America and also Europe. And these features are absolutely huge. So in the example you see below here, they're typically several kilometers wide and can be hundreds of meters deep. And so you note the buildings in this bottom image for scale. And so if you were to walk from one side of these features to the other, it would take you about an hour or so. Now, the world has undergone numerous glaciations over time, and the animation here in the top right of the slide shows the maximum extent of the various Northern Hemisphere glaciations that have occurred over the last 3 million years or so. But looking closer to my own home, the red box here shows how the UK and Western Europe have been covered by ice sheets multiple times during the Quaternary. Now, the largest of these ice sheets to cover the UK reached its maximum extent about 450,000 years ago. And at the time, the edge of this ice sheet would have been just a few tens of kilometers north of London. And this massive ice sheet bridged across the North Sea to join to Europe and covered a similar area to modern-day Antarctica. And as these ancient ice sheets melted, they left behind these gigantic tunnel valley networks carved by all that water being expelled from beneath the ice sheet. Now, the vast distribution of tunnel valleys in formerly glaciated regions could provide analogues, of course, for a future warmer world, tell us a lot about what happens under the ice. However, these analogies are limited because we still don't really know how tunnel valleys form, how fast they form, or even what they do to the ice above them. And several hypotheses have been explained or proposed to explain their formation. So one common one invokes outbursts from trapped subglacial lakes, which carve these gigantic structures in a very catastrophic fashion. And the best evidence we have for this sort of process is that we can sometimes find these gigantic boulder fields at the termination of these valleys, transported by these large flows of water. And you can see a person here for scale next to the size of some of these enormous boulders. Other ideas suggest that the drainage of water from the surface can gradually incise a valley through time, through the actions of these sort of smaller migrating channel networks. And the third idea is the deformation of sediment into these low pressure channels can form these tunnel valleys through kind of a sapping process. So we end up at this point where the answers to these questions can really unlock the full value of tunnel valleys to understand both past and future ice sheet behavior. And so we need to know whether they influenced how ice sheets flow, how they form, how fast they form, but also what their implications could be for the modern day world. And so we turned back to that high-resolution 3D seismic data that you saw earlier and began to peel back the surface of the North Sea to map these tunnel valleys in great levels of detail. And what we began to discover was really quite surprising and really amazing. And that is that we found loads of smaller glacial landforms buried inside these gigantic channels that were completely invisible before. And these you can think of as essentially the footprints of ancient glaciers, visible as seismic reflections buried within these huge channels. And they're really interesting because they can record how the ice was behaving as it underwent extreme melting. So in some channels, we began to find these long snake-like ridges, which are called eskers, and that tell us that water and sediment was being transported beneath relatively slow-flowing ice in the past. And you can see a terrestrial analogy here from Scandinavia on the left. And these features are buried by over 100 meters of sediment and are likely over 400,000 years old. So it's really incredible that we can see them in these stunning levels of detail here. In other valleys, we find these incredibly delicate ridges that were created by fractured ice pushing down on the sediments at the base of the ice sheet. And we see similar crevasse patterns formed by modern glaciers that surge, that is to rapidly accelerate by up to 100 times their normal speed. And these crevasse squeeze ridges are quite small, delicate, and really are not tend to be preserved in the landscape for very long. So the fact that they are preserved within the tunnel valley here shows that ice must have stagnated and wasted away inside these tunnel valleys following a surge in ice flow. In other valleys, we can see these small pits formed by the melting of stagnant ice blocks buried within the valleys. And these pits were probably formed by blocks of ice that initially broke off the main ice mass in shallow water conditions and were then buried by outwash sediments being pumped out from beneath the retreating ice sheet. And in some data sets, we also find these elongated ridges flowing out from the valleys that indicate accelerated ice flow in the vicinity of the tunnel valleys. So why do all these landforms found inside and around tunnel valleys matter for? Well, we can see similar landforms emerging from beneath modern-day glaciers as the ice recedes from the landscape. And this allows us to link the presence of these landforms to the behavior of the ice which formed them. And this means we can then go back in time and infer how that ice behaved in response to extreme melt conditions. And these new observations basically fit into two contrasting categories about how these giant channels impact ice sheet behavior as they're forming. So on the one hand, we find these sort of slow and stable glacial footprints that indicate that the formation of these channels helps to stabilize ice retreat in response to extreme melt. Whereas in others, we find these dynamic and fast features that imply that the formation of these channels help to accelerate the ice, causing dynamic behavior. And so it really isn't a simple story about how the formation of these channels affects ice sheet dynamics during periods of extreme climatic warmth. So at this point, we can answer the first question. So yes, they do influence how ice sheets flow, but in a surprising and quite a complex way. However, these landforms don't answer the question about how tunnel valleys actually form. So we looked carefully again at our seismic data and began to distinguish these smaller sort of braided channel networks at the base of some of the tunnel valleys. And these suggest that this much larger channel was cut by smaller flows of water and helps us to constrain how quickly they were cut and how it might have affected the ice flowing above them. In fact, these braided or abandoned channel structures are quite common within the valleys if we can resolve them in enough detail. And if you remember from earlier, having these smaller migrating channels cutting the broader tunnel valleys is more in tune with the idea that smaller seasonal influxes of meltwater from the surface can carve a larger channel rather than requiring a huge flood. So to test how these observations might apply at the scale of an ice sheet, we modelled how water flowed beneath the last ice sheet to cover the UK and Western Europe. And this image shows the build-up and retreat of the last ice sheet to cover the UK, and it runs between about 31,000 years ago and 15,000 years ago. We use this particular geometry because ice geometries from glaciations further back in time, where most of these tunnel valleys were likely to be produced, are not very well constrained. So this is really where most of the best data was available. And so using estimates of climate warming at this time, we then began to estimate melt rates both above and below the ice sheet and route all this water to the ice sheet margin. And you can see that it forms these channel networks on the right here that flow from the interior to the edge of the ice sheet. And so we then zoom into this area of the ice sheet that used to cover northern Denmark, which is an area where lots of these tunnel valleys are found on land today. We can see that water flows through holes in the surface of the ice sheet and then travels along the base of the ice to reach the ice sheet margin. And our results predict that channels close to the ice sheet margin form with a similar spacing to tunnel valley networks under the sea today. And we then took these water flow rates and put them into an erosion model for a soft sedimentary bed to calculate how quickly these tunnel valleys could form. And the headline number is that it takes just a few hundred years to a couple of thousand years to cut an enormous channel beneath the deglaciating ice sheet. This is because when you funnel all that enormous amount of meltwater sourced from the surface of a melting ice sheet into these smaller migrating channel networks, like we see in our 3D seismic data, you can rapidly erode soft sediments like we find in the North Sea. We then repeated this particular analysis of the erosion with a water flow from a larger flood. And we found that outburst floods from a topographically confined basin can also lead to large-scale channel incision over thousands of years. However, this process is much more likely to yield just a few smaller channels because the discharge you need is enormous. And also this would then require all this refill to occur quite frequently. And so therefore, the main mechanism we think is responsible for the formation of these tunnel valleys is the seasonal propagation of surface meltwater to the base of the ice sheet, flowing in these smaller channel networks, which then gradually incise a larger tunnel valley over time. So we proposed a mechanism for how tunnel valleys form. So first of all, the action of these smaller migrating channels supplied by surface meltwater incises a wider valley, which is mostly filled by ice. And the movement of that ice through the valley helps to enlarge it by triggering mass movements along the valley sides, which we can also detect in our 3D seismic data. Gradually retreating ice can then deposit these laterally continuous eskers within the valleys as the ice recedes, whilst more dynamic ice behavior is indicated by presence of things like crevaceous ridges and lineations in and around the valleys. So we can then tick these two questions off the list. But so far, we've mostly focused on sort of the glaciological implications of this work. But these ancient glacial features are actually key to some of the most pressing issues of our time and are relevant for how we can achieve a net zero society today as well. And this is because the landforms found inside these tunnel valleys, such as this 14-kilometer system of eskers you can see on the right here, frequently contain these very large accumulations of shallow gas, which seem to be particularly or partially connected along the length of these features. And we can see this a bit better if we slice through this image horizontally here. So you've got a 3D seismic section going down through the Earth on the right, and we're taking a horizontal slice through that image on the left here. And what you can see is lots of gas in red highlighted both within the tunnel valleys and also on the right-hand side, a trap between the two valleys. And if we then correlate the location of this gas within the tunnel valleys to the deeper layers where much of this gas actually is commonly found and comes from in the North Sea, we can see that at this location at least, there's no obvious correlation between these features going up. However, elsewhere, we can see clear mechanisms that can allow gas to be transported up into the tunnel valleys from much deeper down, where it could become or potentially move quite quickly along the relatively porous landforms like the eskers buried within them. And so in this example here, you see at the bottom right, the intrusion of a gigantic salt dome has mobilized faults in the overlying layers, which have then allowed gas to move upwards towards those tunnel valleys buried near the seabed. If we then zoom in to that top part, to the near seafloor, we can see that the tunnel valley sediments can both act as a trap for the gas, but also as routes which this gas can escape into the seafloor. And then on the top of the image here, we've got some data from hydrographic data showing actually you can image these methane leaks coming out of the base of the seafloor where these tunnel valleys are sitting. So the presence and migration of gas within tunnel valleys clearly has really important implications for the installation of near-surface infrastructure like wind farms, because these tunnel valleys can represent hazards to their installation. And that is because if you were to incorporate these tunnel valleys into a 3D model of the subsurface, especially if they contain landforms like eskers, for example, if you were then to drill into this, for example, it could cause an explosion. And indeed, there have been previous examples of companies having to resite infrastructure costing millions of dollars because they didn't comprehensively survey the seafloor containing tunnel valleys at the time. Similarly, if you want to try and store CO2, which is carbon capture and storage, beneath the seafloor, if that carbon was to migrate through faults at depths that tunnel valleys exist at, particularly if it's faulted, they could then allow that CO2 to escape through these relatively porous features and potentially be released back out to the seafloor again, limiting the efficacy of carbon capture and storage efforts. And so it's really important, therefore, to consider and properly survey these features when monitoring CO2 leakage from underlying carbon storage efforts, or even radioactive nuclear waste disposal efforts for that matter. So tunnel valleys therefore have implications for the fate of ice sheets under a warmer climate, but also must be considered and properly surveyed when installing renewable infrastructure or attempting carbon capture and storage in environments like the North Sea. So, although they're ancient, these glacial features, now buried hundreds of meters beneath the seafloor of the North Sea, have implications for addressing some of the most pressing questions of our time. Our new 3D seismic data has allowed us to map unexpected landforms that are normally invisible in normal exploration data, and this helps to shed new light on how the Earth's modern ice sheets may respond in a warmer climate. Our data reveal that there was a regime shift in iceberg carving that occurred prior to the disintegration of the UK's ice shelf, and that could be used as a precursor for what may happen in Antarctica in the future. In terms of tunnel valleys, they're the plumbing systems of ice sheets which you can think of may well evolve beneath Greenland or even Antarctica potentially in a warmer world. Our data tells us that the formation of tunnel valleys can affect ice flow in unexpected ways that could both stabilize or destabilize contemporary ice sheets under climate change. And these features may also, of course, pose a risk to the installation of renewable infrastructure or carbon capture and storage efforts in formerly glaciated environments. So with that, I'd like to say a massive thank you to all the wonderful researchers involved in this work, as well as the data providers for some incredible data. I had a really nice group of people working on this data and lots of different collaborations, and so we've been really, really lucky to be doing this, really, and a fantastic group of people. And with that, I'd like to say thank you very much for listening. You can